So then I Gabriela, so you have 15 to 20 minutes, I think, right? A little bit time, and yeah, 15, let's see. And then time for discussion, and then we will go on, yeah.
Yeah. Okay, hello everyone. I would like to share with you about the first working package of my PhD project. It is titled Extreme Rainfall Events in the Tropical Andes by using radar data. So, as you know, extreme events are very important, not only because it affects economic development, but also this affect the human life. So, in this case, extreme rainfall is difficult to analyze because there are some constraints, like, for example, the lack of reliable data, and also because the rainfall is characterized by a high spatio-temporal variability. So in the tropical Andes, it is a challenge to capture this extreme this rainfall variability due to the orography and to the climatic effects. So what do we know about rainfall? We know that in the tropical Andes there is a complex spatial and temporal variability, and usually we use annual, monthly, and daily data, but these are not enough to capture the extreme rainfall events. Also, instruments like rain gauge and also satellite products are used to capture these events, but this has not enough spatial and temporal resolution. So, for this reason, we have a solution. This is the weather radar. In this case, we have an image of the daily rainfall obtained from the CAX radar. It is located in the Cajas in the southern Ecuador, and it captures this rainfall with a high spatial and temporal variability. So the main objective of my study was to analyze these extreme rainfall events and characterize them by using a clustering approach. In my case, I am going to use the K-means algorithm. For that, we use the weather radar data. Regarding materials, we have a radar. It is named CAX. It is located at 4,450 meters above sea level in the southern Ecuador. It covers an area of around 100 kilometers and a spatial resolution of 5 minutes. We use data from around 3 years. About the study area, it is in the Interandean zone in the southern of Ecuador, and we have a bimodal regime in this area with April and October like the rainy seasons, and the average annual rainfall is around 700 and 1,700 millimeters. Regarding methodology, first I have an outline about my methodology. First, I selected extreme rainfall events. For that, I used a daily rainfall threshold. Later, I am going to apply the K-means algorithm. For applying this clustering approach or K-means algorithm, we need to select the features that we are going to use in this algorithm. For that, I used 8 characteristics that I got from the weather radar, in this case in the CAX radar. So we used temporal characteristics like duration, and hydrometeorological characteristics like, for example, rainfall accumulation, intensity, and reflectivity, and spatial characteristics like, for example, the location of the nucleus of the extreme star. Finally, I applied the K-means algorithm. The main idea behind this algorithm is to group the object, in our case, the extreme rainfall events, based on its similarities. So, results first, we selected the optimal number of clusters. In our case, it was 3, because we used an error method, so it gave us this optimal number of clusters. We found 3 classes. The first class, in red class, we got 29 events. In the class 2, the blue color, it is 20 events. And in the third class, the class 3, we got 16 events. Regarding the characteristics of each class, we found that these classes are related with the types of rainfall. That's, for example, convective, stratiform, and mixed. We found, I have 2 characteristics, the maximum rainfall accumulation and the duration of the events. In the case of the first class in the red color, we found that it showed the highest value in the maximum rainfall accumulation, but the lowest duration. In the case of the class 3, it showed characteristics similar to the stratiform behavior. That's, for example, we found the lowest values in maximum rainfall accumulation, but the highest values in the duration. And the second class, the mixed class, it showed a behavior of both rainfall types, so convective and stratiform. Also, something interesting that we found is about the occurrence of these extreme events. We found that the class 1 was more frequent in the last 3 months of the year, but the class 2, it was more frequent in the first months of the year, but the class 3, in our case, the stratiform class, it was through all the year. So it shows us the bimodal regime that we have in our area. Also, we didn't find events in July, August, and September because this not met our criteria to select extreme rainfall events. Another interesting thing that we found, it was the location of the nucleus of the maximum intensity of each storm. We found that the class 1, class 2, in our case the convective and mixed class, it was located in the lowest parts of our area. But in the other way, we have the stratiform, the red colors. It showed that the nucleus of the event was in the highest part of the elevations, in our interandean valley. So, in conclusion, first, we found that this classification was performed by using a data-driven method. It was an unsupervised methodology, and it was an objective classification. Also, we found these 3 classes of extreme rainfall events that show a similar behavior with convective, mixed, and stratiform rainfall. And for my second working package, I am going to identify these extreme rainfall events and which are the main characteristics that trigger the flood events. So, thank you for your attention.
So, well, first my name is Adrián Sucozhañay, and I'm going to change a little bit the extreme. So now I'm going to talk about the Streamflow droughts, what is another important variable in our region. So these results are part of my first working package of my Ph.D. that I'm doing in the University of Cuenca. So the topic is called Characterizing Streamflow Drought Events in a Near Natural Interandean Tropical Catchment. So, first of all, the motivation of this study was that commonly, actually, as we can see in the previous presentation, the tropical Andes is a region recognized with high water availability. Even locally, the population has a very good confidence in the water security. Commonly because we have the presence of these high mountain ecosystems, which supplies water for downstream population across several rivers and lakes and small streams. But there is the question, do we have water all the time? Is this really true in this area? And as we can see in the picture, we can answer that, we can now see that is not completely true. Even in these places, we can see or we can observe the occurrence of these drought events. And commonly, many studies shows that we have actually a high drought vulnerability in the region, which is commonly caused because population in general, and specifically stakeholders and decision makers, are not used to face water scarcity conditions. And additionally, this is also caused because most of the studies that we can find in this area are related to meteorological droughts, using large temporal and spatial scales, and additionally using a standardizing index, which is really good to find the climatological relationships, but we don't know exactly what is happening with the streams. And why is this variable so important for us in this region? And it's because commonly the most water extractions are located directly in the rivers. So if something is happening in the river, something will happen in the population. So in this way, the objective of this study was to characterize streamflow droughts in these inter-Andean tropical catchments. For this, we selected the headwater of the Paute River Basin, which is located in the southern Ecuadorian Andes. It's really important to mention that this basin supplies water for the third most important city, which is Cuenca, and additionally of this, it supplies water for a hydroelectrical project located downstream the headwater. So at a national level, is a basin very important for the Ecuador. In this area, we selected 4 discharge stations distributed in a nested approach, and the highest elevation point is around 4,400 meters above sea level, and the lowest point is around 2,200 meters above sea level. So the red dots in the map are the location of the streamflow gauges, and we can the area to the outlet of this point is around 52 to 1,200 square kilometers. And the data recollected here is around 25 to 52 years of daily data in the period of 1964 to 2016. Then, to accomplish this objective, we established 3 main steps. The first one was to test different methodologies to identify the droughts. So we tested first a fixed threshold and a daily threshold. These thresholds are based in the 5 percentiles of the flow duration curve. And the difference between these 2 types of thresholds is that for the fixed threshold, we use the complete series, the data series, to calculate the flow duration curve. And for the daily threshold, we use the monthly curve, and then we use a daily moving average to obtain the daily values for each day of the year. Then we performed a pooling sensibility analysis using the interevent time. The interevent time is the time between 2 consecutive events. This was a really important step in our region because we have a high variability in the streams. So we need to find a way that we need to be really sure that the event is independent between them, or we have to be very secure that it's really an event or not. Maybe it's just small parts of the event for separated. So then we calculated the frequency of the total number of drought events for each of the interevent times. And finally, we analyzed the monthly variability of these drought events using the event frequency for each month. And we want to do this because we try to compare to the bimodal precipitation seasonality, and to look maybe if the drought events are following the same pattern of the seasonality. So in this area we have 2 wet peaks of precipitation, one occurring in May and the second one occurring in September. So the results. First of all, I'm just going to show some results of one of the stations, and for the percentile of 3 percentiles, the 70, the 90, and the 98. Just for illustration purposes, I have to mention that the results are very similar across the different stations and the other percentiles. So first, we found an interval time of 10 days. After this value, we didn't see a significant change in the frequency of the drought events, and additionally, there was any difference between a daily threshold and the fixed threshold. So we can notice now that we need to wait like 10 days to be secure that the drought events are like merging each other. And then we also check that what was these drought events that like were merging each other. So those were the very short drought events below 5 days, which were like pulled each other. Then with this interval time, we calculate the duration frequency, which is observed in the histogram of the figure. And we can notice that we have a very a short number of drought events. And actually, when we are calculate the mean of the average of the duration, we have values around 23 to, for example, in this case, to 12 days. So this is like really short, but that also that can be the discharge, well, the stream flow could be so low that it's like reaching the 98%. So then the difference between the two thresholds is that for the daily threshold, we found a higher number of the total number of drought events. And for the fixed threshold, we find a slightly higher mean duration. Then we plotted the monthly frequency. Comparing both thresholds, first we found that it was able to detect some anomalies in the wet season that supposedly the temporal months that we have more water, but we can also notice that there is some anomalies there. And we can also notice that the daily threshold was also available or could represent to identify the droughts in the dry season, which is in the late of the year. And to keep looking what is happening in this monthly frequency, we plotted each of the drought events according to the month of when the drought started and the duration of these droughts. So first of all, when we compare both thresholds, is that for the fixed threshold, we notice that most of the droughts are located in the end part of the year. But when using the daily threshold, we notice that these events are scattered around the whole year. But not just that, we can also notice that for the wet season, that commonly we don't expect large anomalies durations, we can see that we have 125 days of droughts, which is very important because of the implication of this is that commonly, or what could happen is that when a season is a drought starting the wet season, it could continue to a normal dry season, which is a less severe scenario for the water management, because you are going to have this anomaly, but you are going to have a normal period of seasonality, of the seasonality in the stream flow. But the severe scenario is that it happens when this drought starts in the wet season, but it prolongates or propagates to a drought in the dry season, which is more severe for the drought, for the water management, because you need to take some action in the wet season that you are not expecting these kind of events, and then you also have to find some ways to manage the water in the dry season. So some conclusion is that first of all we find different characteristics of the droughts compared to another regions. We have a really short drought duration. We can see that in the middle it's across 20 days, which is the maximum mean duration. But it also implies that could be like a new case of the study comparing like in this scientific area, because nowadays are we looking in the global that droughts are like becoming more faster, and so this could be like an interesting point to study because we now have this kind of faster droughts, for example. So we have to take these processes to understand what could happen in another regions when we have this faster drought development and recoveries. And finally, comparing both thresholds, we have the daily threshold. We could identify a higher number of drought events, mainly located in the wet season, and we can also notice that they are really important in the duration of these anomalies in the wet season. And we also could notice that we can detect the start of a drought like earlier in the month. And just finally, some future work, we try to look what is happening, like specifically happening in these drought events that share the wet and the dry season. And then the next part of the PhD thesis is that we want to find what are the drivers or what are the characteristics of the drivers that are controlling these events that we already identified. Commonly, we think that it should be like something related with the precipitation, maybe some days before the drought starts, we can find a relationship with the deficit in the precipitation. Finally, what we want to do is like establish scenarios of precipitation discharge streamflow scenarios to simulate the impact in the drinking water management. So take these like physical relationships to know what is going to be the impact in the drinking company, for example, and then to another project like irrigation, or maybe energy, the sector of energy, and like we can like to keep like playing between scenarios, like making it more severe or with longer durations, and then we can like develop a framework of water management during this condition. So that's all. Thank you for your attention.
Thanks a lot. I think very good in time. So, questions?
Yeah. So, thank you both for your presentation. I will start with you because you were last one. First, I didn't understand correctly. Faster growth, is it frequent or shorter?
Actually, I was thinking that we are going to have in the future more like larger durations, but there are some studies, for example, in the United States, that they found like events that are like the development of the drought is like faster than previous years. So it's like a discussion around the globe between what is happening with what will happen with droughts. If they are like becoming like faster or it's going to have a longer duration.
Awesome. And then second, that I probably missing, and this is maybe this comes from the different fields of the definitions. What is the drought in your case? Can you define what is the drought? Did you invent yourself, or what is the drought in your literature?
Is the drought in the literature using these thresholds is a definition of the discharge that goes below this stream flow level. So this is the definition using this methodology. But commonly we can find a lot of definitions of drought, but commonly is defined like the natural anomaly in the variable that you are studying. For example, precipitation, stream flow, and then you have a more complex definition when you merge for example, temperature, precipitation, soil moisture even, and with all these variables you can define like the spatial like domain of the drought event. So it's going to depend about what variable or what part of the cycle do you want to study.
And the drought that you describe here is a base without the precipitation. Am I correct?
Sorry?
The drought, the definition of drought that you're talking, and show the distribution over the year for each of the month. It's a base with no precipitation or with no water or what?
Streamflow. It's the rivers, the level in the rivers. Yes, it's just in the streamflow variable. So that's why what I want to do next is like find this relationship between the drought in the streamflow in the rivers with the precipitation. So how many days, for example, should be like no rainfall that is causing or producing these kind of events. So in this way you can maybe join this. If you don't have like 15 days of rainfall, you are going to have maybe more frequent this kind of deficit in the streamflow, and this deficit in the streamflow, how much is going to be like the impact on the water management. So, because after the definition of the streamflow, you have to define the water scarcity, which is that you are not supplying enough water compared to the water demand. So the water demand is for the people.
Okay, I will do more.
Yeah, I think that's a interesting point. Sorry. But I was wondering, is P70, 90, 98 percent defined by literature, not by you, right?
Commonly is used is like tested in several studies, but I decided to use this one because so commonly are defined to the point, well, according to the point that the flow duration curve, that is this one over here, so it's according to the point that the tendency of this curve change for the lower water levels of the stream. So commonly you describe this point. But I decided to use both 5 threshold because we don't have any like exploratory study like previously. So we decided to take the 5 of them. So we are like we are really sure that we are having this more like extreme events like are very rare in the occurrence. But we also have like this other point, which is the 70 percentile, that is like more frequent or more or less severe water threshold, drought threshold.
It's interesting part would be at what point of threshold is it going to be a problem? Because I mean 70% could still mean it's no problem at all.
Yeah, exactly. Yeah.
So but extreme value problem like over 99% would be especially a very interesting case.
The more extreme events, yeah. But what was trying to do here is like to look since when are the more extreme events, like in the 80% are like being identified in the previous percentile, like I said. How many of these drought events goes to the 70 percentile and then goes to the 98%? And this we can like use it like also as a warning level. So if you have the percentile, maybe it could be or not an impact, or like we are like not being a severe drought, but you have like to be careful with this. So then when you reach the 90%, to be like more secure that this is a drought event. But commonly, these warning levels are detected by the water demand, because there is where the impact is going to be produced.
I have 2 quick questions. The first is you mentioned the inter-event time. Did you calculate it for each stream in the nested system, or is it like average for all? For each stream. And the second, maybe at the daily approach, having like a moving average is a bit more precise than the fixed threshold. Do you know the difference, the amount of events that disappear from one to the other, so the difference in the number of them?
Yeah, I was calculating this because I am looking for what exactly is happening between these two threshold types, and I noticed that it's around 72%. Is like persisting. So are the same in the fixed and in the daily threshold. So it's a higher amount of the events that are persisting between the both threshold types. So something that I was like testing is how can I use both threshold, because for the fixed threshold we are only going. We will use the fixed threshold. For example, in January, we are going to have a more severe water level threshold for the droughts, but for the wet season, we have a more permissible threshold. So one thing that I was looking how to merge both of these thresholds. For example, if a threshold, if in the wet season, the discharge levels goes very low, below the daily threshold, which is the more permissible, and goes below this fixed threshold, this is an indication that the event is very extreme. So with this, we can figure out merging these both thresholds to identify a new warning level.
Will you be investigating how whether there's a seasonal change? So at the moment you say the wet seasons are, that one, yeah. So the wet seasons are in March, April, May, and September, October, November.
Yes.
Do you intend to also look at the changes when the droughts happen? Whether there's a shift from that there's more droughts in the future occurring, for example, even in May?
Yeah, but I don't know.
So do you analyze the whole data as a bulk, or do you do annual analysis?
I don't understand very well.
So you have your 52 years time series.
Yeah, more or less.
Yeah. Do you analyze whether there's a shift in droughts over the years? So.
Yeah. We didn't check this, but commonly these values were obtained using mostly the same the same precipitation data, the years of the same precipitation data. But I didn't analyze the tendencies of this data. But what I did was check if these thresholds are going to be the same in moving wind. Yeah. So I checked that, and we cannot find a change, too much change in this level. Okay. So that's why we use the whole period of data.
Okay.
But commonly, if you are going to use it in another stream and another place, you need to
first check that.
Yeah, exactly. So. Yeah, because we also think that in future, well, this is something in literature that says that this is what is going to change, the percentage of the threshold that you are going to have already a drought. But for that, commonly they use a merging of also precipitation and discharge, because then you have the relation of the atmosphere of the climate with the response of the catchment. So because for a drought we need both interaction, the climate and the regulation of the basin. Because actually you can also check for the land cover change with this.
I also have a question to you, Gabriela. Yeah. So the time series that you're investigating from the radar is 2015 to 2017 and 2020 to 22. Is the radar still active now, or is it?
Now it's active from May, almost from May of this year, because we have a problem with the connections, especially with electricity. So we have to change this part, but now it is working.
Okay, but it's not operational by the Climate Weather Service, it's by the project from the Ph.D.
fund. For the project, yeah.
Oh, okay. And there is no public radar system in?
No, it is not public because it is operated by Etapa. It is the company of water in Cuenca, and also by Marble University. So it is not public, but
Yeah, okay, I know that this one is not public, but is the Ecuadorian Weather Service that has radar?
No.
So, okay, it's not.
It's only for Cuenca.
Okay.
The INAMI is the name of the in charge of the weather in Ecuador.
Yeah, but they only use rain gauges on.
No radar, they don't have their own radar system, okay.
I just have one suggestion. In your slide, if you can make your slides with the clustering those, and you show that first class related to a lot of water and small duration.
Yeah.
Second class kind of yeah, exactly to that one. So I think it will be interesting if you characterize a little bit more for each class, because for me it's the most dangerous class 1.
I have
because there is the landslides and all this stuff that may occur during the short and a lot of rain.
Yeah, I have 14 characteristics almost. I mean, maximum rainfall accumulation, duration, the location of the nucleus, the amount of occurrence, the hour of occurrence of the events, also the coefficient of variability, the area of the event, but I couldn't put all in this because of the time. But yeah, I show it only like the most important to classify between convective and stratiform. So, but yeah, I got another insight, another characteristics, like for example, the area, the coverage of the area, and also this coefficient of variation and the reflectivity.
No, I understand this characteristic. What I say is that if you generally characterize, and confirm me if I'm correct, the first one is the most dangerous.
Yeah.
Yes?
Yeah.
Compared to the second.
Well, it's not the most dangerous because it is like, yeah, you have the maximum value of intensity, but it has the shorter duration. No. So, yeah, but the class 2 is a little similar, but with lower values of intensity, but yeah, it has a longer duration. So it depends a little about the location, because, for example, if you have this class 1 in other areas, not in the city, but in other areas, it not provoke some problems in the areas, but so I think that it depends on more characteristics.
And actually, when you are studying the landslides in the Andes, commonly it's a combination of both things. You need to have like enough water in the soils, because the soils are like very organic, with organic matter, so you can retain a lot of water in the soils, and then you also need like a very intense precipitation to produce this landslide. So commonly it's the combination of both things. But I think that for the urban case, yeah, you are going to look for only those like very intense rainfall. And actually, just one thing that we notice just these days is, for example, when I have the drought event located in the last part of the year, and the end part of the year, we have like the most intense, this convective rainfall. So this is very important maybe for us, for the water management, well, for the hazard management, because you are going to have maybe landslides, but in the other side, in these same months, you are going to have a drought. So this is like another discussion that we are having, like you need to be prepared for this kind of both things, like very intense rainfalls and very like yeah.
Yeah, maybe you said it in the beginning, but how do you find extreme rainfall event?
Well, first we selected a daily rainfall threshold, in that we used a distribution of wet days. We used that the days that was above 1 millimeter, it was considered like a wet day. So by using this distribution of wet days, we used all the days that was above the percentile 90, above the percentile 90, so that we selected all these days, and later by visual inspection, I was checking where was the rainfall. And obviously it has to have some inter-event time to consider like that is independent spatial in the time.
Okay, so you use 90% threshold then?
Yeah, 9%.
Typically you would not consider to be an extreme event. That's all. Extreme is there actually in the distribution,
Yeah.
very 99%.
99%, it could be considered 99%, but I was checking the bibliography. So in case we got, for example, 67 events, in this case, 67 stream events. If I consider a little higher this percentile, I'm going to get only a few events.
Yeah, of course, it's very extreme. It's like
It was very extreme, but we want to characterize a little more about this stratiform. We wanted to find a little more stratiform rainfall because in Paramo, we are going to
But
find
your also distribution depends on the short period. If it's a larger period, then perhaps the definition of extreme events will be different in that case.
So you would probably say occurrence of types of strong rainfall. Diplomatic answer.
I'm guessing you didn't say, but use like kind of cross-validation. You don't want to use only, or did you just use it once? The k-means clustering?
No,
Because I also don't understand the how you came up with the 3 clusters. I'm still.
how I got the 3 clusters? Well, first I used the elbow method. It is by using the number clusters and the sum of the square errors. So you found this sharp elbow.
This elbow
which is the optimal number of clusters. And also in our area, usually the rainfall is classified in these 3 classes. So it was agreed with our last studies.
Just a suggestion, you could try not to do some kind of cross-validation in this k-means, like leave one out or something like that, and then see if you get a similar robust result.
Is it possible to do with the shorts?
Leave one out, is definitely possible.
That could be something.
Also just an idea.
Yeah, thank you. I'm going to check that.
Are there any questions online?
I don't see any questions, but probably our online participants can also raise their hand and ask questions directly because we have few. No, but probably I have another question regarding the implications of your results, Adrián. So could you please elaborate more how this classification of different droughts can be used in water resources management? You mentioned few cases, but probably elaborate more about implications.
Yeah. Well, this is all about how you are going to classify the events. So this is what I'm working now. I have this first idea that this typology that was already described in previous literature, like this is called the wet to dry season, those events that occur in the wet and then propagate to the dry season. But also I need to check what is happening with this. Yeah, so what is happening with this very to these more extreme events like the percentile 98, where this is maybe just very short durations maybe, but that you have a very low water level. So maybe if these are like too short in duration, but they are causing like the higher impact. And then this is another classification. The other one is this wet to dry season events. And another one that I was talking like a little bit, the combination of these both thresholds when you have a drought event that is like below the fixed and the daily threshold. Because in these cases, you are going to have like is like less frequent to occur in comparing to the whole period of data, and you will also have like is less frequent to happen in this daily threshold that they capture the seasonality of the series. And for then trying to prepare these scenarios, I want to take 1, 2, or 3 maybe examples of this and then put it in a simulation model to know what is going to happen then in the water management. What I want to do there is like put in maybe a WIP model or maybe another distribution allocation water model to look for the impact in the water demand. And also we are like trying to find like, this is another option that I have like for the last part of the thesis, to use like social data, to use like, for example, what is happening with a drought is occurring in the irrigation systems. So to try to use like social indicators to characterize these drought events in the social part. That we are also working with the province governments to recollect some social and economic data for across the city and across the government, some information on this. And then we are like planning to increase these drought scenarios, like making it more severe, like it is going to be like synthetic scenarios, but it's going to have this framework to use it like in future in any case that you are going to know that how you are going to respond. And you also are going to have like already a calibrated model to simulate this precipitation discharge, the stream flow relationships.
Any further? No. Okay. Then thanks a lot to both of you. How long will you stay with us?
June 17.
So still 3-4 weeks or so.
Yeah.
Okay. Okay. Yeah. Thanks a lot. And then see you around. Right?
Yeah. See you.